Hello again, everybody. Today we're going to be talking about our derivative rules. So this is sections 3.2 to 3.4, which is the product and quotient rules, trig derivatives, and the ever-important chain rule. So to start off, we're going to need a couple of limits for some basic trig derivatives, which are a result of the squeeze theorem from section 2.3. We could have technically included these limits back then, but the book likes to include them now when they use them for the derivatives of sine and cosine. So the first is if you have the limit as x goes to 0 of sine of x over x, this limit is equal to 1. And if you have the limit as x goes to 0 of 1 minus cosine of x divided by x, you get 0. Now, these have alternate forms. You know, if I had the limit as x goes to 0 of x over sine of x, this is going to be the same thing. It's also 1. It's just you technically have 1 divided by 1 now, which is still 1. And if you had the limit as x goes to 0 of cosine of x minus 1 over x, you would have the negative of the previous limit, but this is still just going to be 0. So the reason I need these is if I want the derivative of sine of x, I have to apply the limit definition. I get the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Now, when I did this section before, I said that, the stuff that doesn't have h's always cancels away, and then you're left with an h on top and an h on the bottom, and those cancel, and you're able to apply your limit. But here, that doesn't really happen, because the x plus h is kind of stuck inside of the sine, and I can't do a whole lot with it. But what I can do is apply one of my trig properties, or identities. The sum identity for sine is going to be sine of x cosine of h plus sine of h cosine of x minus sine of x all over h. And that's just from this first term here. Now it's a little worse, but what I do see is I have a sine of h over an h, and I'd like to use that if I can, because that matches up with my very first limit identity here. So I'm going to collect some like terms in a way. I have a sine of x and I have a sine of x, and I'd like to bring those two together. I'll have sine of x factored out of those two terms times cosine of h minus 1 all over h plus the term with my sine of h. I'll have sine of h cosine of x all over h. Now I'd really like to be able to use this limit, the limit on just this part right here, but I can only apply my limit if I apply it to everything all at once. So I have to be more careful than that. But what I can do is everything that has an x does not match up with an h. Or what I mean by that is everything with an x is not in terms of h. And so as h is going to 0, technically everything that has an x is unchanging. So it can be factored outside of my limit like so. I'll have sine of x times the limit as h goes to 0 cosine of h minus 1 over h plus, further doing the limit laws, I'll have cosine of x times the limit as h goes to 0 of sine of h over h. And these are precisely the limits I prescribed up above. My limit as h goes to 0 of sine of h over h is 1, and my limit as h goes to 0 of cosine of h minus 1 is equal to 0. So I'll use those. This is equal to 0, this one is equal to 1, so I'm left with 0 plus cosine of x, which is just simply cosine of x. So that's my derivative rule for sine, and I can go ahead and make a chart with the rest of the trig derivatives because they actually come as a result of the quotient rule, which we're going to do next. If I start with sine of x, then the derivative of sine of x is cosine of x. If I start with cosine of x, then the derivative is negative sine of x. If I have a tangent, then my derivative is secant of x quantity squared. If I have a secant, then my derivative is secant of x times tangent of x. If I have a cosecant, then my derivative is negative cosecant times cotangent. And if I have cotangent, then my derivative is negative quantity cosecant of x all squared. The negative is outside of the square for this one. Now, since these limits are included in this section, we can ask you some specific limits for you to solve. We'll ask you a question which looks like the limit as x goes to 0 of 4 sine of 5x all over 3x. And the idea is I want to be able to apply my sine of x over x limit, because as x is going to 0, I have something going to 0 inside of the sine, and it's divided by something going to 0. However, these things are different, and I'd like as much as possible to try to match them up. So since I have a 5x inside of the sine, I want a 5x on the bottom, so I'll multiply and divide by 5, and rearrange my fractions. I'll have a 4 times 5, so I'll have a 20 over 1. We'll just set that out front. I'll have a 1 over 3, because that's the extra 3 on the bottom that I don't want to deal with. Then I have sine of 5x divided by 5x. That's what's left. These constants come out to the front of the limit, and I'm just left with this guy here. I'm allowed to say this limit is automatically 1, but the reasoning for that is there's a little change of variable that happens here. I could rewrite this as the limit as y goes to 0 for y equal to 5x. And this changes to sine of y over y. Because if y is equal to 5x, then y goes to 0 as x goes to 0. This is technically an application of continuous functions where I'm able to move the limit to the inside of continuous functions. But we don't care so much about that process as we do the result. So in the end, my limit is equal to 20 over 3 times 1. For a significantly more interesting example, I've come up with a lovely problem. Let's suppose that I have the limit as x goes to 2 of tangent x squared minus 4 divided by the sine of x minus 2. Now at first glance, this doesn't seem like it's going to be a relevant problem because my x values, they're not going to 0, they're going to 2. And I have a tangent up here, I have a sine, but there's nothing to match up with the sine. But I'm going to go ahead and I'm going to split this tangent because tangent is equal to sine over cosine. So I'm going to have the limit as x goes to 2, and I'm going to write it like this. I'll have the sine of x squared minus 4 divided by the cosine of x squared minus 4 multiplied by 1 over the sine of x minus 2. Now, it's tempting to try to factor this x squared minus 4 into x plus 2 and x minus 2 and then try to cancel it with the sine of x minus 2, but the algebra doesn't really work that way. All the stuff that's inside of the sine up on the top is stuck inside of the sine up on the top, and I can't really cancel it with anything the way it is. But what I can do, since as x goes to 2, if I plug in 2, my x squared minus 4 will be 0. The only problem is I don't have anything to match up with that like I do in the rule I have at first. So I'm going to multiply and divide by an x squared minus 4 over an x squared minus 4. And I'm going to do the same thing for this sign on the bottom. I'm going to have an x minus 2 over an x minus 2. Now I'm going to rearrange all these things in their fractions to group up exactly the way I want them to. With the sign of x squared minus 4, I want the x squared minus 4. So I've taken care of those terms. With my 1 over sine of x minus 2, I want an x minus 2. So I'll have an x minus 2 over the sine of x minus 2. And that takes care of that one and that one. Now what's left is I have an x squared minus 4 on top and an x minus 2 on the bottom. So I'm going to put those together because I know I'm going to be able to do something with that. Because since this x squared minus 4 is outside of the sign, I'm going to be able to factor and cancel that with the x minus 2 pretty easily. So that takes care of that term, and all that's left is a 1 over cosine of x squared minus 4. Okay, everything's accounted for. Since x is going to 2, x squared minus 4 will be 0, and the x squared minus 4 will be 0. And these terms match, and I'm able to use my sine of x over x limit fact. Similar to how I did a change of variable right here, I would be choosing a y equal to x squared minus 4 as part of my argument. But I'm not going to write that part out. Whoa, calm down. I'm not going to write that part out because it's not necessary for our graded work. It's sufficient to just show that they match and they go to 0. So I'm going to split this into 4 separate limits. It is unhealthy to try to evaluate a limit for part of your function and not the rest of it. Instead of writing an x squared minus 4 here, I'm going to go ahead and factor it as x plus 2 times x minus 2, all divided by x minus 2. Now I seem to have run out of room here, so I'll add the last multiplied bit, the limit as x goes to 2 of 1 over cosine of x squared minus 4. Now I can safely evaluate all of these limits separately because I have split them properly using the limit laws. This first one is equal to 1. I have 1 multiplied by the second one is equal to 1 with the same property. The third limit, I can cancel these x minus 2's, leaving me with the limit as x goes to 2 of x plus 2, which is 2 plus 2, which is equal to 4, multiplied by, and then the fourth limit, if I plug in 2, is 1 divided by cosine of 0, and cosine of 0 is equal to 1, so this is also 1, leaving me with an answer of 4. Wasn't that fun? I wish we could have more of those. Moving on, we'll hit our actual collection of derivative rules. The first is the product rule. If I want to take the derivative of a product of functions, then this will be equal to the derivative of the first times the second plus the first times the derivative of the second. Now, I have a lot of freedom writing out my solutions to the product rule. Multiplication and addition are both commutative operations, so any rearrangement of this line is an acceptable, correct answer because they'll be equal. I'm going to generalize this a little bit. If I have 3 functions, for example, then how the product rule ends up working is I need to rewrite this term with a different derivative each time. And what I mean by that is, first up I'll have f prime of x times g of x times h of x plus, I'll write it again, but a derivative of the second function, g prime of x times h of x plus f of x times g of x times h prime of x. So if I have too many things multiplied together and I'm trying to take the derivative, I could end up doing a whole lot of work because I basically have to rewrite it every single time, just changing the term I take a derivative of. After the product rule, we have the quotient rule. The quotient rule is a lot more strict than the product rule because we have a subtraction involved. If I want the derivative of f of x over g of x, this is going to be, it's the derivative of the top first, so f prime of x times the bottom minus the top times the derivative of the bottom divided by the square of the bottom. And last but certainly not least is my favorite, the chain rule. It's most important, I say, because it's the most frequently forgotten step, especially in future calculus courses. It's the source of a lot of lost points. So if I have the derivative of a composition of functions, if I have one function inside of another, then it's going to be the derivative of the outside with the inside function plugged in multiplied by the derivative of the inside function. And this chain rule generalizes to how many ever steps you need depending on how nested your functions are, giving you essentially a chain of derivatives as you move into your function. So we'll finish up by doing problems with some of these. First up, I'm going to do one with the product rule. Not too bad. If I have x squared times sine of x, then I have one function multiplied by another function. So first up, if I take the derivative of x squared, that's 2x times sine of x, plus x squared times the derivative of sine of x, which is cosine of x. Way, way better than trying to deal with the definition of the derivative. Second up, another one of my favorite examples, if I have the derivative of tangent of x, this is actually the derivative of the sine of x divided by cosine of x. So, taking the derivative of the top first, the derivative of sine is cosine of x, times the bottom, cosine of x, minus the top, sine of x, times the derivative of the bottom. The derivative of cosine is negative sine of x, so I'll have a negative sine of x here. All divided by negative, hold on, nope, the square of the bottom by itself. Just cosine of x, all squared. I have cosine of x, quantity squared, minus negative sine of x, so this is actually plus sine of x, quantity squared, divided by cosine of x, quantity squared. And you might recognize this top one here. This is one of our best trig identities. The square of the sine plus the square of the cosine is equal to 1. This is 1 over cosine of x, quantity squared, or since 1 over cosine is equal to secant, this is secant of x, quantity squared. Now I simplified this problem just so it would match up with the derivative rule that we have, but generally when we're dealing with these derivatives involving the rules like quotient rules and product rules and especially chain rules, it's much better, especially for grading, if we don't try to simplify them in any way. Stopping up here with the unsimplified version is a preferable place to stop doing the problem. For the example of the chain rule, I have e to the x squared minus 4x. Now I like to organize these with some lines. First up, I have a function of e to some other function, and inside of that I have a second function. So I know I'm going to need to take the derivative of an e thing, and I'm going to need to take the derivative of this polynomial. It's also helpful if you need to identify how these functions are nested. So I could say f1 is equal to e to the x, f2 is equal to x squared minus 4x, and I could recognize that here, if I take f2 and put it inside of f1, then I'm going to get e to the power of x squared minus 4x. So what I should be looking for in this derivative is the derivative of f1 of f2 of x, which according to my rule is f1 prime of f2 of x multiplied by f2 prime of x. Now, since the derivative of e to the x, or f1, is just e to the x, this is equal to e to the x, but instead of x, I have a function. So I'll keep the inside, x squared minus 4x, and then multiply by the derivative of the inside, which is 2x minus 4. Now, it's entirely possible to have all of these rules happen all at the same time. So let's try to take the derivative of cosine of 9x quantity squared, all divided by x cubed e to the x. Now, what I should recognize first is that I have something divided by something. So first I have a quotient rule. And inside of that quotient rule, I'm going to have a chain rule for the top half, and I'm going to have a product rule for the bottom half. So let's set up that quotient rule. Quotient rule is derivative of the top first. So on the top, I need the derivative of cosine of 9x all squared. So how does my chain rule work for this? I have something squared. Inside of that, I have the cosine of something, and inside of that, I have a 9x. So I should have 2 cosine of 9x times the derivative of cosine of 9x, which is a negative sine of 9x, times derivative inside of that, which is just 9. That's the derivative of the top. And we need to multiply that by the bottom. Minus the top times the derivative of the bottom. Now the bottom here, there's a product. So I'm going to need to do the product rule on that. I'll have 3x squared e to the x plus space. I'm going to cheat. There we go. Don't you wish you could do that? Plus x cubed times the derivative of e to the x, but the derivative of e to the x is just itself. So be careful with dealing with these, because this first e to the x is not a derivative, but this second e to the x is a derivative. And this is all divided by the square of the bottom function. X cubed e to the x quantity squared. So certainly be careful when dealing with your derivatives, and be sure that you're not forgetting any rules. And always check your work. As a further example, the chain rule kind of unlocks some extra derivative rules for us, and that is the derivative of general exponential functions. So if I have the derivative of a to the power of x, where a greater than 0 is a constant, then this is equal to a to the x. It doesn't really change, kind of like regular e to the x, but it's multiplied by the natural log of a, the base. This rule also works for the derivative of e to the x, but the natural log of e is exactly equal to 1. So if I wanted to do something really crazy now, I could ask for the derivative of 4 to the cosine of the sine of x squared minus secant of x to the 4th. That looks pretty nasty, doesn't it? But honestly, I think it probably won't be that bad. So let's try this. First up, I have 4 to a power. Okay. Inside of that, I have cosine of some stuff. Inside of that, I have sine of some stuff. And inside of that, I have x squared minus secant of x to the 4th. Now that's going to require its own little chain rule, even though the x squared will not. So let's see how well I can write this out. The derivative of 4 to a power is going to be 4 to that power. So I'll have cosine of sine x squared minus secant of x to the 4th, close, 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 multiplied by the natural log of 4. And that is multiplied by, let's start it over down here, times open parentheses. I want the derivative of this inside portion. That's cosine of sine of x squared minus secant of x to the 4th. So derivative of cosine is negative sine. Keep the inside. Multiplied by the derivative of the inside of that. The derivative of sine is cosine. Now I need the derivative of the inside of that. So I'll do another line down here. Times, open parentheses, derivative of x squared is 2x, minus the derivative of secant of x to the 4th. The derivative of secant is secant times tangent. So I'll have secant, keep the inside, x to the 4th, times tangent, keep the inside, and to this I multiply by the derivative of the inside, which is 4x cubed. Now I can close that parenthesis, and I can close this parenthesis I started up there. Be very careful with your parentheses on these problems, because as we saw here, there is a difference here, and I want to make sure that I'm multiplying all of the correct things together. For example, this 4x cubed here is only multiplied by this term and not to the 2x, because the 4x cubed is not on the inside of the x squared, or rather, the x to the 4th is not on the inside of this first x squared function. Now, next time we'll deal with implicitly defined functions, and the last of our added derivative rules involving logarithmic functions and inverse trig functions, both of which are technically inverse functions. And then on Tuesday we get to a comfortable start with our new material by looking at some basic natural science examples.